Okay. 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 Yeah, there we go. That's good. All right. Hello, everybody. Just waiting a little bit longer. All right. Very well. Let's get started then now. It's just the one of us at the moment, so on the live video. So, Legion, do you have any questions that you'd like to ask? Just straight up, either in Piazza or on Echo. Let's see if I can quiet down the construction noise outside. Nope. Okay. All right, welcome to week 10. Let's just get started then. And given that there's only one of us here right now, it's probably not going to be a whole lot to discuss. But please do go ahead and ask questions if you do have questions. And I wanted to sort of go over, do a bit of a summary of the various things that we're looking at, and a bit of a conceptual overview. We'll see how we go in terms of examples or questions about examples. Things will make a bit more sense over the next week when we get into the nitty-gritty mechanics of all of this in a bit more detail. At the moment, we've sort of just been looking at a very overview, high-level view of event stream management, and we've got a bit of a better idea about reactive programming at the moment, which is good. So we're starting to look at how that all fits together. All right, what is happening? Programming assignment 3 will be available shortly. Thank you all for your patience. This one's going to be a bit smaller than our previous programming assignments. What with the less time that we have to finish it, it will be due end of week 12, start of week 13-ish. I will make sure everybody has sufficient time on the acceptance tester for it. And yeah, that's going to be about Kafka and streams and functional reactive programming, a bit of all of that in there. So that will be available soon. Yeah, got all of your assignment 2s and starting to have a look at those, which is good. And being an even week, obviously there are no workshops this week. All right, so getting straight into it, what are we looking at this week? Well, functional reactive programming and the unified log, the basics of Kafka, what's going on there. So again, another quick prompt here. Do we have any questions? No questions now. That's okay. I mean, the latency can be pretty nasty on the stream, so fair enough. Is there anything in particular that you'd like to cover today, since you are actually the only person here right now? I know the people watching the recording are going to be like, what the heck is going on? So this week in the functional reactive programming space, we started looking at like real-world applications of functional reactive programming. It's still a little bit abstract and all over the place. So I wanted to spend a bit of time discussing where you might actually consider using functional reactive programming. Because so far we've looked at this idea of event streams, and it's like, okay, well we have like these streams, and we do this processing stuff on the streams. We have like cells, we have streams, and we can perform different operations on those. It might be a little bit hard to get an idea, especially because some of the examples have been a bit abstract that you've seen, and the ones that I've demonstrated have just been raw functional examples of, okay, well, this is how you do this operation, this is how you do this operation, this is what each of these operations do. So I wanted to spend a bit of time discussing why are we doing all of this and where might we want to use this in the real world. So to start off with, a bit of a recap, why are we doing all of this? Well, if we think back to the very start of the semester when we started talking about this idea of events, and we said, okay, well, what are events? Events are sources of input into our system, and the whole way through this course we've been taking a very functional approach to event handling. We've started off with our state machines, and we've drawn up some state diagrams, and we've gone, okay, well then how would we actually code these? We got to the implementing section, and we drew out functions that mapped various events, and each event was a function that could be triggered at any point in time. And the idea was that an event would result in that function being triggered. So we'd write out these functions, and the functions would say, okay, well, we have state, and what do we do with the state? You know, given a particular state, when this event occurs, what do we do? So we had the function for when the event occurs, and what the function would essentially do would be to say, okay, well, the event has occurred, what state are we in, and this is what we do. So we're in this state, okay, well, now do this and transition to this other state. And there were some variations on that. We looked at merely machines, merely more machines, as slightly different variations on how to architect that. So whether that was all right, we're in this state and we've just received this event, so now I'm going to do this behavior, and then I'm going to jump to another state. And that was the base of the merely machine. And then we had the more machine, which was okay, well, I'm in this state, I've received an event, I'm going to transition to this other state, and as I arrive into this other state, I'm going to perform some behavior. But it's all been functional. We have these functions that get triggered when input events come in. And then we had a look at the observer pattern. We talked about dynamic event handling, how we can register these and work with APIs, and then we started to take a look into functional reactive programming. In functional reactive programming, we said, okay, well, let's take a slightly higher overview of all of this. Let's think about events as not just individual discrete things that happen, even though they are, but what could we potentially do with them in terms of treating them as a sequence of things rather than just individual discrete events. And how can we program knowing that we're going to have a sequence of these coming through? And we started to look at the different approaches. So we had the different operations that we can perform on sequences of events as they flow through our system. We looked at the cell structure and the basic approach that that had in terms of this is a piece of data that is constantly changing and will automatically propagate updates throughout anything that is connected to it. And we also looked at the stream, and we looked at the various different operations that we can perform on streams in terms of things like filtering out unwanted events from the stream and allowing the rest to propagate on. And we started approaching our programming in terms of, okay, well, a series of functions that get run one after another, and each of the functions have different operations. And as data propagates through these streams, you can perform these primitive operations, different sorts of transformations and things on those streams, and that changes our data and results in what we want happening. And we explicitly declare all this at the very start, and because it's a very declarative way of writing our code, and because it's designed to be functional from the start, because everything that we've been doing up until this point is effectively functional programming, so it makes sense that the paradigm that we use actually matches the way that we are trying to program these events. So these events would propagate through streams. The streams would be manipulated and transformed by the various functions, and they would all be declared up front, and then we would get our outputs at the end. And that was sort of where we got to with functional reactive programming. So the question is, well, how would we actually apply this in real life? And the book has some interesting examples of that in chapter 4, which is what we were looking at. So they had an example of, I think, a point of sale system and a fuel system. And these are a good start. So to throw it back now, what are some other examples of places where this approach might be useful? The first thing that I'd like to propose or ask us is, where are places in the real world where we might encounter events in terms of programming? Probably everywhere, but can we think of any particular places in programming or examples of programs where we might start to see lots of events? Where do we get lots of events coming from in our actual programs? Write this down on the paper. Oh, that is very twisted. There we go. Where do events occur most often? Or what are some scenarios where we're most likely to get lots of events that we have to deal with? Right, because so much of what we've looked at so far is like very abstract. So for me, the main things that spring to mind when we ask the question of, well, where are events going to occur most frequently, is, I mean, the first thing that I think of, and this is more of a personal thing, is networking. Yeah, anything that has to do with a network is going to be dealing with events, whether it's data coming in, or responses to data that we're sending out, or it's pretty much always data coming in, or just general events on the network, connections, disconnections, those sorts of things. Anything to do with networking is going to be fairly heavily event-reliant code. Networking is one of my areas of speciality, as it were, which is why that's the first thing that comes to mind for me. But you're probably going to be thinking of anything involving user input. That's probably the first thing that comes to mind for most people, and I don't blame you there. That's probably should be the first thing that comes to mind for most people. So networking, user input, anything to do with hardware sensors. So we have sensors, and we probably also have things like system events. Whether those are things like hardware interrupts, which these two are kind of tied together. In fact, these are all tied together in a variety of different ways. Network events are typically triggered by some sort of hardware event, and system events are typically triggered by hardware, and sensor events can typically trigger types of system events. User input, the user interacts with hardware that triggers those sorts of things. But broadly speaking, these are sort of the main areas that you will come across events in the development of different things that you're developing. So any piece of code that has to deal with any of this stuff is going to need to deal with events in some way. So how could we apply what we know about functional reactive programming to each of these areas? Can anyone think of any examples that we might have in terms of networking, user input, sensors, or system events, where specifically the approaches that we've looked at with functional reactive programming might be useful? So broadly speaking, some applications that So broadly speaking, functional reactive programming is especially useful anywhere where we have to deal with streams of events, and where dealing with discrete events, or dealing with events in a discrete manner, is not super efficient. So places where we could use functional reactive programming, any of these. So I'd start to think of things like, okay, well, what about multiplayer games, for instance? We have user input, and we're going to have network traffic that we have to deal with. So things like games. How might we apply functional reactive programming in a game environment? So if I have a multiplayer game with potentially lots of different users connecting, all potentially simultaneously, and all of the users are trying to play online at the same time, in theory. So they're all going to be providing inputs, and then the game that we create has to somehow resolve all of that information into like a consistent game state, so that everybody is receiving the same information, everybody's seeing the same thing on the other end. So, for example, you might have all of the different user inputs from various different users. So let's just say that we have 4 users for the moment. And all of these users are interacting with their clients. A lot of the time we'll be dealing with some sort of client server or peer-to-peer system where we have to somehow resolve the state of the system. So user 1 might be controlling their game character or game player that they're controlling, user 2 is controlling their own, and each of those characters may have to interact with each other, or the actions that one user takes may influence the other characters in the game in some fashion. For example, if you have a game where multiple users are moving around and they bump into each other, what happens? So you may need to resolve all of those inputs and try to determine an appropriate game state at every single point in time throughout the operation of the game itself. So if we have a series of inputs coming from all of the users at various intervals, then what we have is we have a series of input streams from each user. So we have this stream data coming in from each user, and we might want to do things like, that went crooked. We're going to need to perform various different operations on this. So for example, if a piece of user data comes in late from one user, maybe we want to ignore that data. Now, to some extent, the network protocols that we choose to use may do so, but we may also need to resolve that change within our system. So something that we could potentially do is we could potentially merge all of the input streams and provide and perform some sort of merge function on them, so that as the data comes in from every user, we're able to what's the word? As the data comes in from every user, we're able to achieve a consistent game state by looking at the current game state, looking at all of the information that has just come in from all of the users, and then combining that to achieve a single game state. So a very simple system, or a very simple way that you might apply functional reactive programming is, okay, well, if I have all of this information from all of these users, and maybe I'm going to apply some filter to each stream, or alternately I could merge the streams to start with into one big stream of data, but let's start by filtering. So I could apply a filter to all of these input streams, and that filter might do something like, okay, well, let's remove all redundant information out of these streams. So if we get duplicate information, or if we get late information that's no longer applicable to the current state, we can wipe that data out of the stream so that we just get the relevant data that we need. And then we can merge that together with the big merge operation. And our merge operation can perform all of the logic needed to bring all of our different streams together and achieve a consistent game state. Now, that's not to say it's going to be simple and straightforward to write this merge operation. This is where all of the nitty-gritty stuff happens, but we have an operation that is handling all events coming in simultaneously and addressing each of those events and resolving the state of the system against each of those events, so that we have a consistent state at all points in time, which was one of the big things that we've been talking about with events. We've been talking about, okay, we need to have consistency at all points in time. The whole thing that we were doing with state machines was we were saying, okay, let's make sure we know exactly where we are at every point in time and that we can account for every possible input at all points in time. So having a consistent, if we have a multiplayer game, having a consistent game state for each set of inputs as they are received from all of the clients, if we're going for a client-server architecture, and even if we're not going for a client-server architecture and a peer-to-peer architecture, this could be quite relevant as well. So making sure that we have a consistent game state is going to be quite important, and then once we achieve that consistent game state with our merge operation, we can send that information and propagate it back out to all of the clients. So, and this is only a few operations or a few primitives. Now, again, the code inside could be potentially quite complicated, but we have this potential for taking all of this data and condensing it down because we're treating them as streams of data, and we have quite powerful tools for doing that. So that's an example of an application of functional reactive programming. What else? So we've got, let's come back here. So games as an example. You've seen some examples of how we can do this with just general graphical user interfaces. And you've seen probably a lot of this on the web, not necessarily with specifically like Sodium FRP or frameworks like RX, but you've probably seen React and Angular, which apply similar principles, or at least they take portions of the functional reactive programming paradigm to create controls that reflect the data of the system in the same way that cells do, and create interactive systems that respond to changes as those changes occur. So it can be quite useful as well in graphical user interfaces. And you would have seen examples in the book as you're going through, examples of a user interface where the user updates a drop-down box field and that results in other fields being enabled or disabled accordingly, whereas normally you'd have to write some reasonably complicated code to achieve that. And well, not necessarily complicated code, but you'd have to write a specific event handler to handle, okay, what happens when this drop-down is changed, and then that would result in you writing some code that looks something like, okay, well, if value is this, then you need to explicitly enable or disable some other control, rather than tying whether the control itself is enabled or disabled to the state of some variable instead, which is much more declarative and nicer way of doing things in terms of the complexity of the code that we were writing. All right, sensors and system events. Let's say that we have a network of several thousand sensors deployed across, thousands of sites across the country, across the world. Maybe we are a utility company, for example, and we want to monitor the state of various assets that we have. So we want to monitor like all of the power meters in all of our customers' houses, for instance. We're going to be getting a constant stream of real-time information coming back from all of these sensors. That'll again be across the network, but it doesn't necessarily have to be across the network. It could just be that we have, hundreds of sensors connected up to one particular computer or machine that we're dealing with. But a lot of the time it will be across the network, and we might have thousands and thousands of these sensors. How might you resolve the data that you're receiving from those sensors into something that is useful real time? If you have software that is going to take the data of thousands of sensors and combine them together in some form to generate visualizations or graphics, real-time graphics, so that you can easily understand what the state of a system is, functional reactive programming could be good, because we can take lots and lots and lots of streams of data and filter out the information that we don't want, transform the data into consistent formats if need be, merge the data together into single entities or grouped entities, and then output that data to some sort of visualization or to a log or something like that. So lots of different options, and it provides us with quite a powerful tool for doing so. It's not going to be, it's not always going to be super practical, and I realize that it can be quite a challenging paradigm to get your head around at various points in time as you're getting used to it, but it is nonetheless a very powerful tool, an approach like this. So that's me rambling a bit about functional reactive programming and how we might use it in real-world applications, and that's what we're going to be looking at a little bit in assignment 3. We're going to be looking at lots of different streams of data coming in, how we manage those and work with those and get useful stuff out of those streams of data. So, does anyone have any questions that they'd like to ask at this point? I see our numbers have increased ever so slightly. Is there anything specific people would like to ask? About functional reactive programming in general, or about specific functional reactive programming operators? I know we haven't really touched on the switch operator at all. That's a very interesting one. Or the switch primitive. Alright, a quick reminder that you can post a question on Piazza or in the Echo chat if you have any questions that you want to ask for those who have just joined us. Alright, so with that in mind, this idea of lots of streams of data coming in and the ability to perform general operations on those streams in order to filter out data and merge streams together as needed and perform various transformations on that data. And I've been talking about it in terms of data. We can treat data as events, and similarly we can treat events as data in this context. It's a broad overall tool, so whether we are dealing with specifically lots of events coming in from sensors, or whether it's user inputs coming in over a system, or whether it's just a stream of data that is coming in. Maybe it's maybe we have a stream of information from a file that's being sent over the network, for example, which isn't exactly networking events per se, but it is data. And maybe we want to be performing some actions on that, like decompressing it as it comes in, if it was compressed data that was being sent. Again, streams of data, streams of events, all a good application, or all potentially good applications for functional reactive programming. So where does Kafka, where does the unified log and where does Kafka come into that? So you might recall the observer pattern. We've just talked about it, so hopefully you recall the observer pattern. We have this way of setting up our system in a fairly loosely coupled manner so that when you have multiple components of a system, they can connect to each other and explicitly request to receive certain updates and events. And switch to a new page here. And that's all well and good, but it requires us to explicitly code into each of our components a mechanism for subscribing to those components, and then how we explicitly provide updates to all of our subscribers. Now, some programming languages provide their own libraries for this and allow us to extend and build off of those libraries. But as we have seen in the code examples that you will have seen around the place, including the code examples that we've posted on my uni, if you want to implement an observer pattern, you have to explicitly, in a lot of cases, write up the code for handling that. So you have the interface for the, in Java you have the interface for the subscriber, or for the have the interface for the observer itself, and then you have the producer of events, who then has to have code that explicitly is designed to call that interface, and the producer of events also needs to have code to access all of its observers. It needs to have code for the subscription, and also needs to have code for the unsubscription. It helps if your programming language provides you a library for doing this in the first place, but you don't always have that. So it has to be implemented for each and every single event producer within the system. But we can build on this model a little bit further, and that leads us to something called the publish-subscribe model, where instead of providing an explicit mechanism for consumers of events, or subscribers of events, or observers of events to subscribe to you directly and to unsubscribe from you directly, what we instead have is we have an intermediate message broker. So if we draw a possibly horrendous diagram of what I'm talking about, in an observer pattern you have your producer of events, and then you have your listener of events, and the listener subscribes directly to the producer of events. It means that the listener needs to have explicit knowledge of the producer and the interface that the producer provides. So the producer interacts with the listener as an instance of the interface. The listener subscribes directly to the producer by applying the interface. But the listener itself needs to have explicit direct knowledge of the producer and how it works, and it needs to connect directly to the producer. I'm sure I'm using the wrong language for this, but so the observer or listener needs to connect directly to the thing that it is observing, and needs to have explicit knowledge of it, and the thing that is being observed needs to have explicit knowledge of how to, or needs to have an explicitly defined mechanism for talking to its listeners. That can get complicated, and it can result in the kind of software systems where you have like everything connected to everything in various different ways, and it all becomes a bit of a mesh, and it can get a little bit crazy because you have different entities that are all listening to each other, and they all become quite tightly coupled, even though one of the points of the observer pattern is to allow for more loosely coupled systems because everything isn't hard-coded together. But we still end up with this mesh of stuff going on. So how do we deal with this? Well, we have another model called the publisher-subscriber model, where you have an intermediate broker. And this provides a consistent mechanism that all of the event producers have a consistent mechanism to send their events on different channels. So you can have typically have different channels. Producers will send their events to specific channels, and then subscribers, or producers or publishers, and then subscribers will talk to the broker, and we have a broker here, and they will explicitly say, I want to subscribe to this channel that has these particular events on it. It doesn't necessarily know what events are on a channel, but you have different channels and producers that connect to a channel, and they emit events and data on those channels. The subscribers subscribe to those channels and they receive those events. So potentially this also means that you can have multiple producers connecting to the same channel if you wanted to, and they're all producing on one single channel together, rather than having to have your subscribers or listeners connecting individually to each producer that they want to listen to. The producers can all transmit onto the same channel together if they want. And the interfacing between them all happens through the broker. So you have a consistent interface across the board. This is what's known as a message broker type system, or a publisher-subscriber model, or pub-sub model, depending on your terminology. But this is a very powerful system, and there are a variety of different ones of these out there. You might have come across, for example, Mosquitto, and the one that we're looking at in this course is Apache Kafka, which is specifically designed around something called a unified log. And the unified log is a smart version of a broker that maintains a consistent log over a particular time period and allows for subscribers to join at any point in time and effectively synchronize with each other by joining in at a specific point in time, consuming events at their own rate, and syncing up with each other and disconnecting when they need to. And part of this model that Apache Kafka provides is a stream API for specifically dealing with events as streams. And that's something that we're going to be looking at, and we haven't quite gotten there in the book thus far. That's stuff for next week. But that's essentially an overview of what hopefully you're starting to get a picture of when you look through event streams in action. As you'd probably be aware, the unified log provides a variety of additional features and systems, and Apache Kafka is loaded with a whole bunch of stuff. Not all of it that we will be using, as you can imagine, but the unified log provides things like generalized logging, redundancy of data, and also tools for maintaining consistency of data as it travels through the system. And also it's designed for working with distributed systems across clusters. So it's not just that it's a standard message broker, because there's plenty of those out there, but it is a system that is designed to deal with very large volumes of events and data coming through, distributed across a variety of service clusters all over the place, to act as a central management and repository of all of the event data traveling through a whole bunch of different systems that form whatever software system that you are trying to design. So that is an overview of what we've been looking at over the past few weeks, why we've been looking at it, and hopefully that makes some sense in terms of what we're aiming for. And we will be looking more at the specifics and the coding of that over the next week. So, does anyone have any questions that they would like to ask about anything that we just discussed? Or anything else, for that matter? I'm hoping I'll be able to post a follow-up video later this week with some more code examples to prep us in for next week. And also to help everybody get started on Prac 3 once that gets released. Okay, well, that's it for the moment then. Again, lots of theory, less practical stuff this week, but lots of code examples coming next week. If you have any questions, please, again, ask them on Piazza or message me on my uni, and I will try to respond as quick as I can. And yes, thank you all, have a good week. And we will catch you next week.